Hotter than the sun. You thought of a star. It's not a star. Neither supernovas nor jets from black holes. The record for heat doesn't reside in space. It is born here, beneath our feet. For a microscopic instant, we opened a window into the first microsecond of the universe. Trillions of Kelvin. Matter melts into its primordial form. Protons and neutrons break apart. What remains is an ocean of quarks and gluons. If it exists, why doesn't it all burn? How is that possible? Today you'll discover where the hottest day in the universe is and why. Fasten your seatbelt. What you call heat is about to change its meaning. If it's not the sun, then where? Hotter than the sun. And it fits inside the Earth. You heard right. Hotter than the luminous skin of our star. It's not a mythical furnace. It's not a hidden volcano. It is an instant created by us in a subterranean ring where heavy atoms race at almost the speed of light and collide like cosmic anvils. For a blink of time that can't even be contained in a clock, matter forgets who it is. Protons and neutrons break apart. What remains is a primordial ocean, loose quarks and gluons. Trillions of Kelvin burning away the very idea of limits. You can't touch it. You can't see it with the naked eye, but you can feel it in the trail of light, in the particles that betray the perfect crime of heat. It's like opening a crack to the first microsecond of the universe and peeking into what existed before the stars were born. How is it possible to create a fire that humiliates the sun? Why does this heat exist, and why does it last so little? If it fits inside the Earth, what else can fit inside what we think is impossible? Today, we're going to descend into this underground of lightning and answer where the hottest day in the universe is born and why. Where is, after all, the hottest day in the universe? Think fast. You imagine the sun, a supernova, maybe a black hole jet. But what if I told you that the place that holds that title is an object in the sky, and that the day wasn't a day at all? The answer begins with another question. What makes something hot? Concentrated energy, glowing particles. Now multiply that by billions, by trillions, and finally, by a fraction of a second so short it escapes the clock. The hottest day was actually an instant. The newborn universe, when all of reality was an oven, and also small flashes recreated by us in underground tunnels colliders, where nuclei collide at the speed of light and create a sea of quarks and gluons. Why does this matter? Because there, in that unimaginable heat, the rules governing matter change. Protons cease to be solid. Fundamental forces behave differently. Clues to what happened in the first microseconds of the cosmos are revealed. So the question bifurcates. Where did it happen, the beginning of the universe and our laboratories? And why? Because only under these extreme conditions does matter reveal its most intimate layers. The promise remains. We will follow the trail of this heat from the primordial explosion to the chamber of a collider and understand, step by step, why the hottest day is not just a scientific curiosity, but a window into the origin of everything. In this video, I'm going to reveal a secret that defies intuition, a heat that surpasses the surface of the sun and fits inside the Earth. You will see evidence, numbers, images, and reports of experiments that show temperatures of trillions of Kelvin for fractions of time so short that even a clock doesn't register them. I will explain, step by step, where these subatomic fires originate, why they occur, and why this instant tells us the story of the first microseconds of the universe. If you think you understand what hot means, prepare yourself. What comes next will shatter your certainties and transform the way you see the cosmos. Short version 1012 South. For quick insertion onto the hook, I'm going to prove that there is a heat stronger than the sun produced by us for an instant and explain why this thermal flash is, in fact, a window into the birth of the universe. Temperature is just hot or cold. Temperature is agitation, the invisible dance of particles. Imagine a hall. When people are seated, everything is calm. That's low temperature. When the music explodes and everyone is running, jumping and hitting things, that's high temperature. In the subatomic world, the people are electrons, protons, and atoms. The more energy they receive, the faster they move, and the stronger the collisions. Temperature is an average of this microscopic energy. Some particles may dance faster, others slower. The number that matters to us is the average rate. In solids, atoms vibrate in place. In liquids and gases, they move and collide. In plasmas, The particles are so energetic that the electrons separate from the nuclei. That's why we say that a flame, a lightning bolt, or the interior of a star is hot. There, the agitation is brutal. We measure this agitation in Kelvin. 0 Kelvin means almost complete. Stillness, each degree above that is more movement, more collisions. So when we talk about trillions of Kelvin, it's not just a high number on paper, it's a hall where everyone is running so fast that matter itself loses its shape. Temperature equals energy in motion, that simple. Powerful. And the key to understanding why the universe can sometimes be an absolute blaze. The surface of the sun, what we call the surface, is the photosphere. It shines for us at about 5,800 Kelvin, about 5,527 C. It is the visible limit, the luminous skin we see in images, and that colors our days. But if you think that the further away from the center, the colder it gets, you're wrong. Leaving the photosphere, we ascend to the corona, the sun's outer atmosphere, and it's an enigma. There, the gas reaches millions of Kelvin, typically approximately 1 to 310 K, or close to 1 million to 3,000. 0 C. In other words, the corona is hundreds to thousands of times hotter than the surface of paradox. That burns our intuition. At the heart of the sun lies the core, a pressure and fusion reactor, where the temperature reaches approximately 15 million Kelvin, approximately equals 14,999,727 C. There, gravity compresses matter enough to force protons to fuse into helium, releasing energy that sustains the entire star. Why is the corona so much hotter than the photosphere? This is the question that still keeps scientists awake at night. Clues point to the solar magnetosphere, magnetic field lines that bend, break, and release energy, magnetic reconnection, and to waves that transport energy from the interior, upwards alpha waves and hundreds of microscopic nanoflowers that together heat the atmosphere. There is still no final consistently strong evidence, and observations from missions like the Parker Solar Probe and Solar Orbiter that have been mapping these invisible flares. Visualize it this way. The photosphere is the skin, hot and glowing. The corona is an incandescent mantle that stretches for millions of kilometers and burns much hotter. The core is the invisible furnace that fuels everything. Each layer obeys different rules, and each explains why heat in space is not a single thing, but a collection of extreme processes. A lightning bolt can reach temperatures of around 30,000 Kelvin. That's right, in a column of ionized air. The temperature reaches much higher levels than the surface of the sun. But why, then, don't you go baking when the sky streaks across the sky? Because heat is just a number, it's time, volume, and transfer. The lightning bolt is a flash of plasma, a narrow, fierce blade that exists for a mere breath. The energy is concentrated in a thin wire. It burns inside, ionizes the air, emits light, and explodes under pressure, thunder. There's neither enough time nor enough mass to transfer heat by conduction to your skin. The real danger is not the thermal baking, it's the current, the electric field, the discharges that pass through everything in their path. In practical terms, lightning incinerates the air from the inside and creates a shock wave. You feel the sound, you feel the impact, but not the furnace. It's a microscale stellar fire, brutal, instantaneous, and localized. Understanding this difference is understanding why our bodies and our intuition lose their bearings when faced with the extreme scales of the universe. This changes the way we see reality. When you realize that the extreme is not abstract, that trillions of Kelvin have already existed, and we have managed to recreate a fragment of it, the world ceases to be just appearance. We came to see that matter has layers, that the laws we thought were immutable are emergent conditions, and that what seems impossible is merely a matter of scale and time. Understanding this primordial fire transforms curiosity into a map. Where did we come from? How's the universe organized? And why do small windows of heat carry answers to gigantic questions? Ultimately, it's not just science. It's an invitation to look at everyday life with different eyes, fewer certainties, more questions, and a clear sense that the universe is bigger, stranger, and, ironically, more comprehensible than it seems. When a giant star runs out of fuel, its core collapses in a fraction of a second, and unimaginable temperatures are born there. Billions of Kelvin. The collapse converts gravity into heat. Matter is compressed until the core becomes a reactor of pressures and shocks. The rebound shock that travels through the stellar layers heats the gas to billions of degrees. It is this thermal bath that transforms light nuclei into heavy elements, neutrinos, in an almost invisible rain, transfer energy, and help inflate the explosion, while the ejection of the outer layers creates shockwaves that burn and incinerate from within. In this fleeting inferno, gold, uranium, and other heavy elements are born. The periodic table itself bears this signature. What we see is a colossal sight, a star exploding, spewing light and matter, and leaving behind a compressed core, a pulsar, a neutron star, or a black hole. The temperature doesn't last. It's a violent thermal snap that forever shapes the surrounding space. Supernovae are the quintessential cosmic furnace, billions of Kelvin, that write the chemical history of the universe in just a few seconds. When two neutron stars collide, the universe makes a crackling sound that burns like nothing we've ever known. They orbit each other frantically, squeezing spacetime until they collide, an impact that heats the gas and scrape material from the surfaces to tens to hundreds of billions of Kelvin. In localized regions, this heat originates from brutal compression, violent collisions, and the accretion disk that forms around the remnant. It is pure energy transformed into heat, neutrinos, and radiation. The result is not just fire. Relativistic jets can be launched, producing bursts of gamma rays. Waves in the fabric of space rive as cries of gravity, detectable billions of light years away. In the fiery corridors of the ejecta, extreme nuclear processes, so-called, our process forge the heaviest elements: gold, platinum, uranium. In seconds, we have a cosmic forge that rewrites the periodic table. In minutes, the light from the kilonova reveals the material launched into space. Temperatures don't last forever. They are bursts of heat on a microtemporal scale, but their signature is profound. Gravity, heat, and nuclear physics meet and tell us how the universe crafts its treasures. Understanding these collisions is understanding how extreme chaos is transformed into matter. And cosmological history. When matter falls toward a compact object, a black hole or a neutron star, it doesn't plummet silently. It forms an accretion disk, a hellish whirlpool where friction, compression, and magnetic fields convert motion into heat. The inner layers of this disk become like an oven, temperatures scaling to millions, sometimes hundreds of millions of Kelvin, with ionized particles dancing in a plasma so fierce it glows in X-rays. But the real spectacle happens when the disk and the central object begin to communicate through the magnetic field lines. Cosmic magnets twist and pull, stripping rotational energy and focusing it into narrow beams. These are relativistic jets. These jets shoot matter and fields at speeds close to that of light racing, like spears through the galaxy. In internal collisions within the jet itself, and in the impact between the jet and the surrounding environment, energy is transformed into extreme heat and radiation. Accelerated particles, photons of extremely high energy. When these conditions occur in a colossal and instantaneous way, gamma ray bursts, GRBS, are born, flashes that for seconds outshine an entire galaxy. Imagine a narrow wire carrying more energy than hundreds of millions of suns, compressed in seconds, delivering photons of such high energy that they traverse the universe. The effective temperatures in the shock regions can reach billions of Kelvin, and the magnetic fields act like pistons that shape and recolorize matter. What we see as GRB is the visible tip of an almost invisible engineer burning disk, and a mechanism that brutally directs that burn into a jet. After the flash comes the tail, the afterglow in radio, optical, X-ray shows that tell us the angle of the jet, its energy, and the density of the environment. These phenomena not only show what extreme heat does to matter, they scatter elements, trigger interstellar shock waves, and for a moment, transform the surrounding space into a physics laboratory that defies our intuition. Accretion disks and relativistic jets are, in short, the universe's most violent language for saying, here there is too much concentrated energy to remain still. When we say gigantic numbers, it's not a figure of speech, it's a ladder that climbs by powers of 10. The sun's photosphere is at approximately 5,800 K. The corona jumps to 10 K. The sun's core rotates at around 1 5 times 1 oka supernova pumps gas at 10 ek billions per second while recreating nuclear reactions that forge heavy elements. Neutron star mergers and violent collisions in the ejecta reach 10 to 10K in localized regions. Gamma rays and processes that create gold are born there. Accretion disks and their inner layers burn at 10 to 1 OK. But in collisions within relativistic jets, the effective temperatures can rise to 10K or more. In laboratories, colliders have reached scales on the order of 10e² 1 OK trillions of Kelvin for fractions of time so short that we only detect traces in the particles produced. And above all that, there's the primordial past, in the initial moments of the Big Bang. Temperatures theoretically exceed trillions, reaching domains where we speak of limits such as the Planck Temperaturian astronomical and essentially theoretical number. But note, high numbers don't mean the same thing in every context. Volume, density, duration, and the type of emission, thermal glow versus non-thermal processes, change the physical meaning of these K values. In short, the universe is full of fires on scales ranging from millions to trillions of Kelvin numbers that shock the imagination, and yet, each one exists under its own rules and limits. When we want to create a fragment of primordial fire, we don't point a torch at the sky, we accelerate atomic nuclei to nearly the speed of light and send them colliding head-on. At Brookhaven National Laboratory, our HIC beats gold against gold at CERN. The LHC throws lead ions against each other in a ring hundreds of meters wide. These collisions concentrate immense energy into a tiny volume with a subatomic psi. Matter ceases to be solid, protons and neutrons break apart, and quark-gluon plasma is born. QGP is an incandescent soup where quarks, which are normally trapped inside hadrons, swim freely among gluons. The temperatures reached are trillions of Kelvin, orders of magnitude above the surface of the Sun, but last only for absurdly short fractions of time. Even so, in those moments the behavior of matter changes. The fluidity, the pressure, the way particles emerge from the chaos tell us about the forces that govern the universe. In its first microseconds, how do we know it exists? Not because we see the QGP directly, it disappears before we can look at it, but through clues. Jets of particles that fade out as they pass through the soup, jet quenching. Collective patterns of particle flow and signatures in the detectors that only make sense if behind them there was an unconfined state of matter. The detectors measure tracks, energies, and coincidences. Physicists reconstruct, as in a cosmic crime, the event that left these traces. Creating QGP is, in itself, an archaeology of time. By reproducing conditions from the beginning of the universe, we test theories about quark confinement, phase transitions, and how fundamental forces behave in extreme regimes. It's a question that's both practical and existential. By igniting the subatomic fire, we learn how matter organized itself and why the world we know emerged from those first burning pages. Remember, QGP gives us a fragment of the most absolute heavier than the Sun, but it's heat that fits into a tiny point and lasts for a blink of the universe. This proves that, when it comes to extremes, our tools and our curiosity can recreate, in fleeting moments, the very beginning. Trillions of Kelvin, think of it as a heat that defies your intuition. In heavy ion collisions, the energy per particle rises to orders of magnitude that transform the content of matter. We are talking about approximately 10 to 10 Kelvin values, where the typical thermal energy per particle corresponds to tens to hundreds of MeV, hundreds of millions of electron volts. It is a fire whose thermometer does not measure melanoma, but rather subatomic energy sufficient to free quarks from their usual confinement, and it lasts for a breath of the universe. We are talking about time scales on the order of a yoctosecond, that is, 10 seconds. In practice, the hot state created in a shock occupies a minuscule volume and lasts for fractions of a yoctosecond to a few tens of yoctoseconds, depending on the energy and size of the system. To compare, a yoctosecond is more than 1,000,000 times smaller than a femtosecond. It's the time in which a proton barely has a chance to escape. Even though it is fleeting, this heat leaves its mark. Particles emerge with collective patterns. Jets lose energy as they pass through the soup, and detectors reconstruct the event like someone reading the fingerprints of a fire. In short, Trillions of Kelvin per yoctosecond is heat in its purest and most extreme form, brutal, concentrated, fleeting, and it is this flash that opens a direct window to the first moments of the cosmos. Imagine an ice cube made not of water, but of tiny beads, each one attached to the next by invisible threads. These little balls are the hadrons. The threads are the force that holds them together. Now place that cube in an oven that doesn't heat gradually, but explodes with heat. It doesn't melt water. It breaks down the bonds. The threads that held the little balls together become sequences of sparks. The little balls no longer exist as separate blocks. They open up and release tiny colored swimwork quarks that previously lived only in groups. It's like heating a chocolate bar over a flame. First it holds its shape, then the surface softens, the layers merge, and finally the solid transforms into a glistening, freely moving soup. In our case, the soup is chocolate. It's an incandescent sea of quarks and gluons particles and the strings that carry them, boiling so intensely that the previous identity disappears. Another image. Imagine an underground prison. Hadrons are cells, quarks are prisoners. At normal temperatures, the doors are locked. When the heat rises to an extreme, the locks explode and the cells collapse. The prisoners scatter across the courtyard and begin to run freely. For a moment, the entire system becomes a chaotic market of particles. Thus, melting hadrons is this poetic and brutal transformation. Composite forms disintegrating, bonds breaking, and a primordial ocean where fundamental constituents float freely. A glimpse of what the universe was like shortly after its birth. Calling this Big Bang archaeology is not an empty metaphor, it's literal. The Big Bang didn't leave a diary. It left physical signatures, particle distributions, flow patterns, jets that fade into the middle, microscopic fossils of primordial heat. When we accelerate nuclei and cause a collision, we are not just creating a small explosion, we are recreating, for an instant, the same density and temperature conditions that existed in the first microseconds of the universe. The particles that emerge from that subatomic soup carry information, energy, momentum, correlations, just as bones and artifacts carry information about a buried civilization. Detectors are our excavators, physicists, archaeologists. They use trails, energy deficits, jet quenching, and collective patterns to reconstruct the event and infer the properties of the state that existed before matter froze into protons and neutrons. This is how we transform fleeting flashes into history, fragments of the past translated into curves and histograms that answer questions about quark confinement, phase transitions, and fundamental forces. Like Edmond Halley, who compiled observational records and discovered that comets repeated their path across the sky, scientists are piecing together collision marks and proving, through evidence, that behind them lay a fragment of the primordial furnace. Each event is a layer of cosmic sediment, each signature a clue. By piecing them together, we read what happened in the beginning, not with stones, but with particle sand. That is why these experiments are, in fact, archaeology of the Big Bang. In the fractions of a second after the Big Bang, the universe was an ocean of pure energy and constantly transforming elementary particles. Temperatures exceeded trillions of kelvins, K values so extreme that no form of matter, as we know it, could exist. The physics that describes this state lies on the boundary between quantum field theory and general relativity, fields that are not yet fully unified. The universe in the first fractions of a second during the first 1043 seconds, the so-called Planck era. Temperatures were higher than 1030 to 1030 decay in this regime. But for fundamental force, gravity, electromagnetism, and the strong and weak nuclear force could be unified into a single primordial force. No current theory can fully describe this moment. With the expansion and initial cooling, around 1036 seconds later, the temperature dropped to about 1027 K. It was then that cosmic inflation is believed to have occurred, an exponential expansion that enlarged the universe in a tiny fraction of time. At that time, thermal energy was so colossal that particles and antiparticles were constantly appearing and annihilating each other, the formation of the fundamental building blocks of matter. When the universe reached temperatures on the order of trillions of kelvins, that is, 1012 K, Near 105 seconds after the Big Bang, the era of quarks and gluons began. In this primordial plasma, particles were free before combining to form protons and neutrons. Modern laboratories, such as the Large Hadron Collider LHC, attempt to recreate this exotic state of matter for microseconds, reaching temperatures close to 1013 K. From Halley to modern cosmology. Although Edmond Halley (1656 to 1742) is best known for predicting the return of the comet that bears his name, his scientific spirit illustrates the transition between observational astronomy and modern cosmological thought. Halley lived in an era when the universe was seen as immutable and centered on the Milky Way. He was one of the first to record systematic changes in the sky, a prelude to the understanding that the cosmos is dynamic. If Halley had access to contemporary cosmology, he would be amazed to learn that the fixed stars he observed formed billions of years after those phases of inconceivable temperature. Halley's curiosity and scientific rigor represent the basis of the investigation that, centuries later, would lead to an understanding of the thermal and energetic origins of the universe. There's a point at which heat ceases to be merely energy in motion and becomes an enigma. Physicists call it the Planck temperature, approximately 1416 1030 to 1416 1032 Kelvin's value is so extreme that the very fabric of space and time becomes unstable. Above it, the known laws of physics, forged by human experience and the most precise experiments, simply cease to function. It is not a dogma, but a limit of understanding, a boundary between what we can describe and what we can only imagine. If we consider the early eras of the universe, moments after the Big Bang, it is plausible that such temperatures existed, not as a literal fire, but as a density of energy that dissolved any notion of particle, distance, or time, matter, radiation. The very concept of before and after became blurred. The Planck temperature thus marks the horizon of physical thought, a place where perhaps new, still inconceivable ideas await discovery. In contrast, Edmond Halley, living in the 17th century, looked to the sky with rudimentary instruments, but with the same unease before the unknown. By calculating the orbit of a comet that would return long after his death, Halley proved that the cosmos was governed by predictable mathematical laws. However, if he were among us, he might be fascinated to learn that there are regions of the universe where predictability breaks down, where the laws we know dissolve like ice before primordial heat. Thus, between Halley's telescope and Planck's equations, there is a continuity, the search for meaning in the face of the unattainable. The Planck temperature is not a forbidden boundary, but a mirror that reflects our limits and, at the same time, our audacity in trying to surpass them. It is the measure not only of absolute heat, but of the infinite curiosity that has always driven the human mind. Not everything that glitters reveals its true warmth. In the sky, light deceives the senses and sometimes even reason itself. What we call brightness temperature, a measure of a body's luminous intensity, is not necessarily its thermodynamic temperature, the one that describes the intimate and chaotic movement of the particles that compose it. These are two ways of looking at the same phenomenon, one through appearance, the other through essence. Brightness temperature is the heat that is seen, the heat that radiation suggests to us. A body may appear intensely hot, emitting light at high frequencies, but its internal energy may tell a different story. Thermodynamic temperature, on the other hand, is the heat that actually is measured by molecular agitation, by the balance between energy and matter. While the former belongs to the domain of perception and observation, the latter belongs to the domain of physics and profound reality. In Edmond Halley's time, stars were judged solely by their splendor. Brightness was synonymous with grandeur, twinkling a clue to divine power. Halley, however, was one of the first to suspect that the sky was dynamic, changeable, quantitative. Behind the light, there was movement, orbit, cause. He did not possess the instruments to measure stellar temperatures, but he possessed the eye that separates phenomenon from appearance, the nascent scientific gaze. Today we know that a star can appear cold and be incandescent inside, or appear fiery and yet emit less energy than its brightness suggests. The sun, for example, exhibits a brightness temperature different from its effective temperature. and even more distinct from the energy released in its nuclear depths. Light is merely a thermal, mask, and incomplete translation of what is happening inside. If Halley could see with the eyes of modern astrophysics, he would understand that starlight is a coded language. The brightness temperature would be, for him, a kind of cosmic illusion, a clue that demands interpretation, like a comet crossing the sky, beautiful, fleeting, but bearing a greater secret. And perhaps he would smile, realizing that even in the universe, as in the human mind, not everything that illuminates reveals what truly burns. Comparison is an age-old human gesture of measuring the unknown by what is already known. But in the realm of unimaginable temperatures, where quark-gluon plasma QGP dissolves matter into its most fundamental particles, the habit of comparison becomes a trap. QGP is a state in which protons and neutrons, building blocks of matter, break down, releasing previously confined quarks. In this regime, the very concept of substance loses its meaning. And without substance, what is there to compare it to? Comparison requires common criteria, a shared language between what is observed and what one wants to understand. When physics reaches temperatures of trillions of kelvins, there is no more iron that melts, no gas that expands, and no solid that resists. Matter becomes a sea of pure energy. It's like trying to compare the sound of thunder with the silence of a vacuum booth, real, but belonging to different realms of being. Therefore, comparisons in the field of QGP require more than just numbers. They require a philosophy of method. Edmond Halley, in his 17th century, understood the value of discernment. When he compared observations of comets and realized they followed repeated trajectories, he was not deceived by appearances. Where others saw omens and celestial phantoms, Halley applied the rule of reason. His criterion was movement, not brightness, orbit, not wonder. With this, he revealed that the comet was a traveler obedient to the same laws that governed the planets. What Halley did with the visible sky, modern physics does with the invisible. It defines the criterion before comparison. Thus, when QGP is studied in particle accelerators, we do not compare it to fire, nor to molten metal, but to carefully delimited theoretical models equations that respect the boundaries of the possible. Only in this way does the comparison make sense. Only in this way does thought not unravel like the very matter it attempts to describe. Comparing, then, is an act of humility before reality. Halley taught us to measure the comet through calculation, not belief. Contemporary physics does the same when confronting primordial plasma, because, in the end, without criteria, all comparison is merely wonder, and wonder, however beautiful, does not explain the universe. There is a silent irony at the heart of the matter. The more we try to liberate it, the more it closes in on itself. Quarks, the elementary particles that make up protons and neutrons, live trapped in an invisible prison, sustained by the strong nuclear force ioni of the four fundamental forces of nature. No experiment has managed to isolate them, and perhaps none ever will. It is the enigma of quark confinement. The more we try to separate them, the more intense the force that binds them becomes. Unlike magnetism, where attraction weakens with distance, the force between quarks grows as they move further apart. It's like a spring that stretches infinitely, until the energy of separation creates new quark pairs and isolation dissolves into multiplication. The universe, at this level, seems to have chosen cohesion as its fundamental law. Even the primordial chaos of quark-gluon plasma, that fiery state of the cosmos' first microseconds, lasted only an instant before confinement restored form and structure. Matter, after all, was born from containment. The four fundamental force, gravity, electromagnetism, the weak force, and the strong force, make up the fabric of cosmic interactions. Gravity shapes the stars. Electromagnetism governs light and chemistry. The weak force transforms particles, sustaining the brilliance of stars, and the strong force, in turn, stitches together the core of reality. But none of them shows itself with such obstinacy as the strong force, invisible, intense, unsubmissive to intuition. If Edmond Halley could hear about these confined quarks, perhaps he would smile with that rational wonder that moved his generation. He, who calculated the return of a comet and showed that even the errant one followed predictable laws, would recognize the same principle here: a cosmos governed by unseen forces, but which determine the visible. In his time, Halley saw gravity as the invisible link between worlds. Today, we see the strong force as the invisible link between particles. The scale has changed, but the mystery remains the same. Ultimately, quark confinement is not just a matter of physics, it's a metaphor for knowledge itself. The deepest truth remains unified, resistant to dispersion, requiring tools, thought, and patience to be touched. And perhaps, if Halley were among us, he would say that each returning comet and each quark that resists solitude reminds us of the same principle. The universe is sustained not by what is liberated, but by what remains connected. The universe was born perfect, and for that very reason, it had to cease to be. In the first moments after the Big Bang, energy and matter coexisted in absolute symmetry, no privileged direction, no difference between forces, no distinction between particles. It was such a total balance that nothing could evolve. And then, in a moment of apparent imperfection, the symmetry broke. The cosmos shattered into possibilities. From this primordial imbalance, the fundamental forces separated: gravity, the strong force, electromagnetism, and the weak force, each gaining its own identity. It was this rupture that allowed the formation of quarks, atoms, and much later, stars and ourselves. Perfection shattered, and from that fragmentation, diversity was born. The universe discovered, through asymmetry, the path to creation. In modern laboratories, physicists recreate tiny replicas of that original instant. Under colossal pressures and temperatures, exotic states of matter emerge: quark-gluon plasma, Bose-Einstein condensates, superconductors, quantum liquids. Each one reveals a new mode of organization, an unexpected response from nature to imbalance. These are forms that defy intuition, where matter seems to abandon everyday rules and behave like pure energy geometry. If Edmond Halley could witness such phenomena, perhaps he would see in them an extension of the same reasoning that led him to predict the return of a comet. He knew that the apparent regularity of the heavens concealed small imperfections, and that it was these imperfections that revealed the profound laws. Just as an elliptical orbit breaks the symmetry of a perfect circle, so too does the universe deviate from perfection in order to exist. Halley, with his mind focused on celestial harmony, would have understood the cosmic lesson of modern physics. It is asymmetry that sustains reality. The breaking of symmetry is therefore more than a physical concept. It is a narrative about the very act of existing. The universe did not choose the repose of equality, but the risk of difference. And in every exotic state of matter, in every particle that behaves improbably, the same principle echoes, that the beauty of the world is born from imbalance, and that, from Halley to the present day, understanding the cosmos means accepting that order is the child of disruption. Before there were stars, before time could be measured, the universe was already writing its own story in the language of energy, density, and light. The first pages of the cosmos were not written with ink, but with radiation. They are silent pages, written in the heat of the Big Bang and preserved in the vibrations of space that we now call cosmic microwave background radiation. These clues are not words, but echoes, minute variations in temperature and density that tell how matter began to come together, how gravity sculpted the invisible into form. Each photon of this radiation is an ancient letter, traveling for almost 13.8 billion years, bringing us the first chapter of existence. Modern astronomers read these markings with sensitive instruments, like someone deciphering fragments of a manuscript erased by time. In cosmic microwave maps, we discover the seeds of galaxies, the signatures of primordial inflation, the first rhythm of matter. Science has learned to translate heat into history, to transform noise into memory. But this interpretation is not new in spirit. Edmond Halley, long before radio telescopes and cosmic probes, already understood that the sky was a moving archive. He looked at comets not as omens, but as witnesses. He saw, in their cycles and returns, the persistence of time. He was the one who realized that the firmament is not static, that the universe, even in the eyes of the 17th century, already told a story. If Halley could observe the sky today with our instruments, perhaps he would seek not only the brilliance of the stars, but the whisper of the beginning, the almost imperceptible murmur left by the primordial expansion. Perhaps he saw in the radiation spectra confirmation of something he had always sensed, that the cosmos is legible, that there is order in the abyss, and that each measurement is a translation of what the universe wrote in the beginning. The clues about the early pages of the universe are not limited to what we have detected. They extend to what we have not yet been able to read. Between each photon and each cosmic silence there are blank spaces, intervals where perhaps the missing words lie, that which precedes matter, that which sustains time, that which makes being. And in this quest, the same one that guided Halley under the London sky and guides physicists under the sky of antennas, humankind continues as an obstinate reader of a book that never ends trying to understand. Who wrote the first verse of light? In the beginning, the universe was not space, but a fever, a concentration of energy so dense and so intense that all matter, time, and the very idea of form were fused into a single incandescent instant. The temperature surpassed any imaginable scale. Trillions upon trillions of Kelvin furnace of pure radiation, where quarks, gluons, and light coexisted like notes of the same vibrant chord. But the cosmic fever didn't last. The universe, instead of burning itself out, began to expand, and in its expansion, it found its first equilibrium. Heat dissipated, radiation lengthened, time slowed down. Each cubic centimeter of the newly born space became a little colder, a little emptier, and in this cooling, the conditions for everything that would come after were born. Matter solidified from energy, atoms formed from plasma, and light previously impersonate began to travel freely. The initial fire gave way to transparency. Today, billions of years later, the echo of that original heat still travels through space. It is the cosmic microwave background, radiation, the thermal murmur of a universe that was once a flame and is now a breeze. Each photon we detect is a reminder of when the cosmos fit into a drop of pure energy, and already carried within it the destiny of stars and conscious beings. If Edmond Halley could contemplate this history, he would see in the expansion of the universe the same logic that he discovered in comets. Order within movement. Halley understood that the sky is not a fixed scene, but a system in transformation, that the return of a comet, the displacement of a star, are traces of an invisible harmony. Similarly, the cooling of the universe is the inevitable consequence of a cosmos fleeing from itself, obeying laws as simple as they are mysterious. Halley, who lived in a time when infinity was merely a philosophical idea, might have been fascinated to learn that the very coldness of space is a vestige of absolute heat, that every particle that vibrates silently in the vacuum today is a descendant of an explosion that never ceased, it only spread, transforming fire into distance and distance into time. The universe, after all, did not die from the heat, it matured in the cold, and we who observe it are merely remnant sparks of that primordial furnace, a conscious, fleeting, and still trying to comprehend how fire became sky. Imagine a stove that, instead of heating the surrounding environment, moves away from itself, taking with it the flames, the heat, and the very air that feeds them. As it expands, the fire lengthens, the heat dissipates, and the entire kitchen transforms into a vast silence. That's how the universe is. In the beginning, the cosmos was this primordial stovia, compact, dense, fiercely hot furnace. Each point contained all the energy that would one day form the galaxies. But what made it what we know today was not the permanence of heat, but rather its expansion. As it expanded, the universe began to cool, as if embers were moving away from each other, unable to maintain the same intensity. Space dilated, and with it, light itself stretched, transformed from incandescent radiation into a cold echo, the almost imperceptible murmur of cosmic background radiation. It's a sublime paradox, the fire that stays lit precisely because it moves away. The cosmic heat did not disappear, it merely spread out, dispersing into the vastness, diluting its intensity to give way to form, balance, and life. If Edmond Halley could contemplate this metaphor, perhaps he would understand it with the serenity of those who observe time in great cycles. He, who calculated the return of a comet and showed that movement is not chaos, but ordered repetition, would see a greater harmony in this cosmic furnace. In his century, the sky was fixed. For Halley, it began to move. Today we know that space itself moves not around something, but fleeing from itself, like a fire that only exists because it disperses. And there is poetry in this separation. Every star, every planet, every thinking being is a result of this expansion. We are sparks from the initial hearth, traveling with it, never to return to the center that originated it because that center no longer exists. The universe is a kitchen without walls, a heat that refuses to stay in one place. Perhaps Halley, gazing at the heavens, was saying what modern cosmology only confirms, that the cosmos does not grow cold from exhaustion, but from generosity because, by distancing himself from himself, he makes room for existence. They say the sun is the limit, but for Edmond Halley, the limit never existed. Centuries before technology, modern telescopes, or NASA, a man looked up at the sky and he saw the future. While the world believed in mysteries and superstitions, Halley believed in something even more dangerous. The reason? He did not see the universe as something unattainable, view it as a code waiting to be deciphered. It was Halley who convinced Isaac Newton to publish his ideas about gravity. Without him, we might never have heard of Principia Mathematica. And it was Halley who dared to do something impossible, predicting the return of a comet, a streak in the sky, seen by kings and peasants alike, which everyone called a divine sign. But Halley didn't see an omen via an orbit, a pattern. He calculated everything by hand. No computer, without a telescope. There's no guarantee it's correct, and yet he said he will return in 1758. Edmond Halley died before he saw the comet return. But when the light crossed the sky, 100 years later, humanity realized he was right. The comet passed by, and Halley's name was etched in history, not in the rocks of the earth, but in the space itself. He didn't just look at the sky, he understood. And that is why, when someone says that the sun is the limit, remember, Halley looked beyond the sun and left his name traveling forever among the stars. The sun is not just a star, it's an open wound in space, an ocean of fire boiling at billions of degrees Kelvin. And yet, in the midst of all this fury, nature is precise. Mathematics, balanced. Edmond Halley looked at that flame and saw more than just light. He saw a code, a rhythm, a heart that beats in the same rhythm as the universe. While everyone feared the unknown, Halley was trying to understand him. He believed that the cosmos was not chaos, but rather order disguised as mystery. He measured the tides, the winds, the orbits, and discovered that even what seems unpredictable, it follows invisible laws. Nature is not just beauty, it's a calculation. It is fire, gravity, and silence and harmony. Each ray of the sun, each wave of the sea, every comet that streaks across the sky, it's part of the same equation. Halley saw life this way, a divine experiment where even mistakes reveal purpose. When we look at the sun and think of destruction, Halley via energy. When we look at space and see emptiness, Halley via movement. He believed that understanding nature, it was about understanding ourselves. Because deep down, we are also made up of billions of kilometers, of heat, chaos, and harmony, of reason and mystery. And maybe the greatest discovery of Halley's castle may not have been a comet, but the certainty that, in every atom of the universe, there's a bit of awareness waiting to be noticed. Nature is not distant, she is the mirror. And Halley, he was one of the first to see the reflection. There are places in the universe where heat is just fire. It's a creation, trillions of degrees Kelvin, temperatures so absurd that the matter itself, it falls apart. This is the realm of QGP, the quark-gluon plasma, the oldest and most primordial form of the universe, a state that existed only for a fleeting moment, right after the Big Bang, a moment in which everything we know, atoms, stars, bodies, ideas that didn't exist yet, energy only, pure chaos, infinite possibilities. And yet, from this chaos, order was born. Edmond Halley never saw a particle accelerator, but he believed in the same idea, that the universe, however violent it may seem, it follows precise laws. 9-part even in extreme heat. There is symmetry, that the cosmos is not an accident, it's an expanding calculation. Today, in laboratories on Earth, humans recreate this primordial hell. They create plasma in milliseconds, trillions of degrees, as hot as the early universe. And what do they find there? It's not destruction, it's the origin. Particles dancing like memories of creation, echoes of the first moment. Halley looked to the sky searching for patterns. Today, we look inside the atom for the same reason. Because understanding the beginning, it's about understanding destiny. Modern science ignites many big bangs in the laboratory. But Halley's gaze, he was the first to realize that nature is a repetition of itself. From comet to particle, from the sun to plasma, everything vibrates at the same frequency. A search for meaning. Perhaps, if Halley were here, he would say that the QGP is not just matter on fire, it is the mirror of the birth of time. And that, deep down, every time we look at the cosmos or into an accelerator, we're asking the same old question: where did we come from? And what keeps us existing in this cosmic laboratory called the universe? There was a day when the heat didn't burn. He created a day without yesterday. No watch, without a shadow. The first day, the hottest day of all. Trillions of degrees, matter and energy mixed together in a single scream. An entire universe, born in silence. Time began there, not with a tick, but with a burst of light. Everything that exists, the stars, the planets, us, is the echo of that moment. And centuries later, a man looked up at the sky and realized that the stars were not just fire, they were memories. His name, Edmond Halley. While everyone else saw the sky as destiny, Halley viewed it as a thing of the past. Each point of light, a reminder of what we were. He understood something profound. Observing the universe, it's like traveling through time. When a comet streaks across the sky, it's not just a show, it's a souvenir, a trace of the same fire that created us. The hottest day is not over yet. It continues, diluted among the stars, no sun, in every atom of our body, because we are still made from that explosion, from that initial light, from that first morning. That's when time started running. Halley believed that nature holds its own truths, in cycles. What is born, returns. What goes away, comes back, just like the comet that bears his name. Perhaps that's why he dedicated his life to understand the movement of the sky, because deep down, he knew. Each orbit of a comet, it's the universe remembering where it came from. And every time we look up, to the distant glow of the stars, time begins to be reborn. The hottest day, it's still happening inside us. If, for a moment, you felt your chest warm up, it wasn't just emotion, it was the universe. I recognize you, because there is something in us 10-part an ancient spark that vibrates every time we understand that we are part of something bigger. That's what Halley felt when he looked at the sky and saw order in the chaos. When he realized that comets were not signs of the end, but promises of a return. He understood that navigating the unknown, it's not about arriving somewhere. It's about continuing to look, keep questioning, keep lighting it. And if hearing this has awakened something within you, a shine, a desire to know what else is out there, so you're already part of it. You're on the same crew that gazes into infinity and feels no fear, it feels like a purpose. The same crew that believes that curiosity is a form of faith. Science and mystery, they are two halves of the same gaze. So remember, you don't need a telescope to explore the cosmos. Just keep asking, because as long as there is someone searching for answers, Halley is still sailing, and the universe, it is still unfolding. If this sparked something in you, you're part of our crew.